Hello, students, and welcome back to our topic on nuclear chemistry. And today we're going to finish up our notes, I think, on this topic of nuclear chemistry. So hopefully you have reviewed your notes from yesterday, you watched the video links that I provided for you, and you are ready to go with your books open. So let's get to it. We left off yesterday with nuclear stability, or I should say, this is where we're picking it up here today. Nuclear stability. You may recall from yesterday that radioactivity is basically the release of matter and energy from the nucleus of an atom that has become unstable as a result of an imbalance between the neutrons and the protons within the nucleus. Well, the converse of that is stability. And nuclear stability is what is achieved with elements or the atoms of elements that are not radioactive, and it has to do with the strength of the nucleus. If an element is not radioactive, then the strength of the nucleus is strong enough to hold the nucleus together. And the name that we give to that is called the binding energy. Binding energy is the nuclear force that holds the nucleus together. Now, to illustrate that, I want you to think about this. I have a tissue here. Let's pretend that this tissue represents the binding energy in the nucleus of an atom. And I have a little mass, a little brass mass here. And if I place this little brass mass into the tissue, well, the tissue is strong enough to hold the little brass mass. I'm trying to hold it so that you can actually see it here. But the little brass mass is in there, and the tissue is strong enough to hold it. You can see it by the evidence of the tissue hanging down. That's where the mass is. So the tissue here is representing the binding energy, and the brass mass would be the nucleus. Now, if I were to use a bigger brass mass like this one in the same tissue and try to lift the tissue up, you can probably guess what's going to happen. Oh, that hurt. Oh, right on my lap. That brass mass went right through the tissue and onto my lap because the binding energy wasn't strong enough because the mass of the nucleus was too great. It's kind of, it may be a poor analogy. It actually certainly was a painful analogy to my lap. But when there's an imbalance between the protons and the neutrons in the nucleus of an atom, the binding energy isn't enough to hold it together and things fall apart. And that's what we call radioactive decay. Radioactive decay is when an unstable nucleus breaks down and releases that energy and matter into the surrounding area, into the environment. And we call that radioactivity. But the process is called radioactive decay. So here we have an example of a parent nucleus that is evidently unstable. The binding energy isn't enough to hold it together, and so it undergoes decay, changing the nucleus into a different nucleus. Now, depending upon what kind of decay is taking place, this may actually change the identity of the very element's name. In other words, radioactivity can change one element into another element. It's something that the precursors to chemists, those that called themselves the alchemists were looking for secret potions and procedures that they could change unprecious metals into precious metals. In other words, changing things from one element to another. Well, we have discovered that that is in fact possible. We can change, or nature can change, one element into another through this radioactive decay. Now, there are two types of decay that we're going to discuss here. And again, we start off with a parent element, an isotope in particular, an isotope with a different number of neutrons than protons. And radioactive decay takes place, producing a different element and releasing heat energy in the process. This is how a nuclear power plant works, by the way. We'll talk more about that in the next topic. So back to the two types of decay. First type of decay probably sounds a little bit familiar. It is called alpha decay, and it is the release of an alpha particle. And just by way of reminder from our last lesson, an alpha particle is made up of two protons and two neutrons. So we may start off with a parent nucleus, and when there is a release of an alpha particle, two protons and two neutrons, the resulting nucleus is going to have a different makeup. The resulting nucleus, called the daughter nucleus, is going to have two fewer protons and two fewer neutrons. It's going to be a smaller nucleus by a factor of 4. Two protons and two neutrons. That's going to be really important here in a moment. But first, the second type of decay, which is called beta decay. And notice the symbol for beta decay, same as we talked about last time. But a beta decay is the release, and this is a little bit more complicated, so follow me here. It's the release of an electron and a proton, which comes from the decay of a neutron. So here's the deal. We have our parent nucleus. In this case, it's an isotope of thorium, thorium-234. But if this thorium undergoes beta decay, look what's being emitted, a beta particle. And again, a beta particle is an electron and a proton that comes from the decay of a neutron. So it gets more complicated than this. The resulting daughter nucleus is still unstable and ends up releasing a gamma ray, and the daughter nucleus has a different makeup than the original parent nucleus. So let's try and summarize this in tabular form, because it might be easier for us to work with the numbers this time around. So here are our two types of decay, our alpha decay and the beta decay. And we're going to illustrate what happens to the mass and the number, the atomic mass and the atomic number during both of these decays. Remember, earlier in the year, we learned about atomic mass and atomic number. And by way of quick review, the atomic number is equal to the number of protons in the nucleus of an atom, and the atomic mass is equal to the number of protons plus the number of neutrons. So let's see how that all ties in here. So to begin, during alpha decay, the atomic mass is reduced by 4. Why? because it's losing 2 protons and 2 neutrons. So if you take 2 protons and 2 neutrons out of the equation, out of the atomic mass, well, that's a net loss of 4. The atomic number, however, the atomic number is reduced by 2. Why? Because you're only losing 2 protons. Remember, once again, atomic number is the number of protons. Atomic mass is the number of protons and neutrons, which is why during beta decay, the atomic mass actually stays the same. Why? Well, you're losing a neutron, but you are gaining a proton. Think about it for a moment. You're losing a neutron, so the mass would go down by 1, but you're gaining a proton, so the mass goes up by 1. So there's no net gain or loss in the atomic mass. The atomic mass during beta decay stays the same. Check out what happens with the atomic number. Again, beta decay, you're losing a neutron, so that doesn't affect the atomic number at all. But from that neutron, it's turning into a proton. And because it's turning into a proton, you're gaining 1 with the atomic number. So the atomic number actually goes up with beta decay. Think about that. Review this summary table and study it for your lab tomorrow and the quiz. All right, so let's move on here. Here's a little diagram that is a graph that shows the trends of decay and the band of stable nuclei. Now, I'm not going to ask you to memorize this, but if you look at it, some of you might be able to grasp what's going on. On the x-axis, we have the number of protons. On the y-axis, we have the number of neutrons. Generally speaking, if you have the same number of protons and neutrons to a point, you've got a stable nuclei and it's not going to fall apart. But there comes a point, and you'll notice the curve here starts to increase a little bit more, meaning the more neutrons that you have compared to the number of protons, well, instability begins to occur. And the more neutrons you have than protons, an atom will generally encounter instability and result in beta decay. That's what the symbol here is representing, beta decay. So in this green category, we've got atoms of elements experiencing beta decay. Now over here in the yellow zone, when we've got elements with, say, more than 84 or so protons, this is when we start to experience alpha decay. This zone here is when we would experience the capture or the emission of electrons in order to sustain more nuclear stability along this red line. If that doesn't totally make sense to you, don't worry. Just memorize the chart and you'll be fine for our purposes. Now, that brings us to the next major category, this topic that we have to address before our lab activity tomorrow, and that is what is called half-life. Half-life. Half-life can be described as the time it takes for half the number of unstable atoms to decay. I will link you to a video that will show this to you in a unique kind of a way. So be sure to check out the linked video after you watch this lesson. But half-life, let me try to explain it to you in some different ways here, beginning with this diagram. Let's say we've got a container filled with pennies. Let's just say they're radioactive pennies. And we start off with 100 pennies. And after a period of time, half that number of radioactive pennies decays. How many pennies will you have left? Or will you have left? Boy, I can't speak. My brain is a little radioactive today. If you start off with 100 pennies, after a certain period of time, half of those pennies decay. How many pennies are you left with? Hopefully you said 50. So when there are 50 pennies left, that would be called 1/2-life. The time it takes for half the number of unstable atoms to decay is called the half-life. So whatever that time frame is, we're just calling it a half-life right now. In 1/2-life of radioactive pennies, 50 pennies disappear from the original 100. Well, let me ask the question in another way. Let's say you've got 50 pennies left, and one more half-life takes place. How many pennies will remain? The answer is 25, or half of the previous number. So after another half-life, half of the preceding number has decayed, so now we're left with 25. Now let's say another half-life period expires. How many pennies are you left with now? Well, the correct mathematical answer would be 12.5. But in nuclear chemistry, we don't really work with halves of atoms. So you might say you're left with 13 or 12. Another half-life goes by. How many pennies would you be left with? 6. Now, if we plot those numbers in this graph, you probably will be able to see what's happening here. The graph is decreasing in a curve. It's getting closer and closer to zero with each half-life, but it actually never becomes zero. In other words, with half-life, it can take a long, long time for a radioactive element to decay. Now, there is a famous radioactive element called carbon-14, which is illustrated in this next diagram, which is actually used to date historic and prehistoric documents and artifacts. And we have found that it is a pretty effective and a pretty accurate timepiece, a radioactive timepiece. And through lots and lots of tests, we have discovered that carbon-14 has a half-life of about 5,730 years. Well, what does that mean? Well, what that means is if a particular sample starts off with a 100% concentration of carbon-14, and we'll call that 100 grams of carbon-14. And after one half-life on our graph, and one half-life is 5,730 years, so after 5,730 years time, half of the original amount of that carbon-14 is left. or 50% of that radioactive element is left after one half-life. After two half-lives, 25% of the original has decayed. After three half-lives, 12.5% of the original radioactive element has decayed, and so forth, creating that same curved graph illustrating half-life. So here's a half-life graph. We've got the half-lives on the x-axis and the percentage of the radioactive element remaining on the y-axis, and it always produces a curved graph, no matter how long or how short the half-life of an element might be. And we'll discuss that there are some atoms that have half-lives of milliseconds, and there's some elements that have half-lives of thousands, millions, or billions of years. So depending upon the element, this graph may extend on for a very long period of time. Our lab activity tomorrow will further explain the whole half-life concept. So if you're a little bit lost right now, don't worry. I think it will become as clear as mud tomorrow during our lab activity. I do want to continue with a third major component of today's notes, and that has to do with what is called nuclear notation. We have learned so far this year about chemical notation. We've learned about subscripts and coefficients in chemical equations. Well, this week we're exploring a different type of equation, and it is a nuclear equation, which has different types of notation. So in your notes, please make sure you write this down as accurately as you can. We start with the symbol of an element, which remains the same. The symbol of all of the elements are the same, whether we're talking about just chemical notation or nuclear notation. But instead of subscripts to the lower right-hand corner of a symbol, we have two other numbers in nuclear notation. The subscript on the left is the atomic number. And the atomic number is equal to the number of protons. That hasn't changed. Atomic number is the number of protons. So when you see a symbol of a radioactive element and you see a number, a subscript to the lower left, that number is the atomic number and it tells you how many protons there are. But above that, we have a nuclear superscript. A superscript is written above and to the left of the symbol, and that number corresponds to the atomic mass. And the atomic mass is equal to the number of protons plus the number of neutrons. So this number 288, for instance, is equal to the number of protons plus the number of neutrons. So keep that in mind as we continue on to examine what is called a radioactive decay series. Check this out. It's pretty cool. We might start a radioactive decay series with a radioactive element like uranium, and we would refer to this uranium as uranium-288. This is an isotope of uranium, a radioactive isotope. And so we identify the isotope based on the atomic mass. But it's identified as the element uranium because of its atomic number. If you look at the periodic table, the atomic number identifies the element. So uranium, no matter what isotope you're talking about, always has the atomic number 92. That's how you identify elements, by its atomic number. Now, here's the cool deal. Because with radioactivity, with radioactive decay, with beta decay with alpha decay, we've got nuclear changes taking place. Now, in this radioactive decay series, we see that uranium-288 is undergoing alpha decay. We know that because I've drawn it for you. I'm not going to ask you to memorize this, but I am going to ask you to try and follow it and understand it. During alpha decay, I want you to think about the chart from the beginning of this period. What happens to the atomic mass and what happens to the atomic number during alpha decay? Look at the chart. Think about it. If you see that the atomic mass decreases by 4 and the atomic number decreases by 2, that's exactly what happens. And that's where these numbers come from. So when you've got uranium-288, it undergoes alpha decay. Because of alpha decay, the new atomic mass is 4 less at 284. The atomic number is 2 less at 90. And because the atomic number changes, we have formed a totally different element. When uranium-288 undergoes alpha decay, it's no longer uranium. It becomes a new element, element number 90, and if you look on your periodic table, that element is thorium. It becomes thorium-284. We call it thorium-284 because it's a radioactive isotope that's about to undergo another radioactive decay of a beta decay. And that beta decay results in, look at your chart, what happens to the atomic mass? Nothing, because remember, you're losing a neutron, but gaining a proton. And because you're gaining a proton in beta decay, what happens to the atomic number? It goes up by 1 and forms a new element. I'll let you find this element on the periodic table of elements. I'll give you a hint. It's element number 91. Look it up and you tell me what it is. And this radioactive element then also undergoes beta decay. Notice what happens to the atomic mass and the atomic number. And look at this. It forms uranium again, but not the same kind of uranium. It's not uranium-288. It's a different kind of uranium that we call uranium-284 that continues to undergo decay and so on until eventually it forms lead. If we have time, we'll explore that a little bit further. But since we're running short on time, I want to finish with 2 more words here: fission and fusion. Fission is the splitting of an atomic nuclei, and this typically takes place with a large element or the nucleus of a large element, such as uranium-235. Uranium-235 is a huge nucleus, has a huge nucleus for this element. And if you bombard that uranium-235 with a neutron, you just toss a neutron at it, and it causes this uranium-238 to fall apart very quickly and violently, releasing an enormous amount of energy And radioactive decay causes the uranium-235 to fall apart into potassium-92 and barium-191, both of which are radioactive, and you lose 3 new neutrons, which if you go back to the beginning and you've got a lot of uranium-235, those 3 neutrons will cause 3 more atoms of uranium-235 to decay, and so on and so on. It causes what is called a chain reaction. And we'll learn more about that next week when we learn specifically about nuclear energy. But for now, I just want to introduce this concept of fission, the splitting of an atomic nucleus, and our final word here, fusion. Fusion is the combining of atomic nuclei, and fusion is generally what happens with smaller atoms. And this is the type of energy that is released in the sun. We have hydrogen isotopes that are being fused together, and they fuse together to form helium and the release of a neutron and an enormous amount of energy. So basically, the bottom line for today, all you have to remember is fission is the splitting apart of a big nucleus. Fusion is the combining of 2 smaller nuclei. And that's where we're going to leave things for today. Again, we'll learn about those 2 words a lot more next week when we explore nuclear energy. But for now, this is all we need to know for tomorrow's lab activity. So I will say bye-bye.